All right, hello. Hope everyone's doing well. We're back again with some more calculus content, and I'm quite excited about today's lesson. We're going to be continuing our discussion on integrals, so hopefully you're up for that. And yeah, we'll jump into it. Hopefully you're having a good day thus far, and everything is going all right for you. So yeah, we're going to be talking about definite integrals today. So we have been exposed to what are called indefinite integrals, and that's just what we've seen thus far, where we have, like, for example, integral of x squared dx, and hopefully now we're comfortable enough to say that this is equal to 1/3 x cubed plus c. So definite integrals are very similar to indefinite integrals. We will see their differences shortly. But one of my favorite parts about definite integrals is that this pesky plus c term goes away. We don't have to worry about it anymore for definite integrals. But first, let's figure out what are definite integrals. So indefinite integrals, which is what we're used to, they're used to find the antiderivative of a function. And as we said, there could be an infinite amount of antiderivatives for any function. Definite integrals are used to find the area under a curve. In particular, we're going to be finding the area under a curve of a particular function by taking the integral of that function. So on the left here, we have our indefinite integral that we're used to seeing, the integral of some function f of x dx. And on the right, we have a definite integral, integral of f of x dx. The difference is that now we have this a and b term here. So usually a and b are like constant values. And what this is saying is we want to compute the integral of this function from point A to point B. And evaluating this will give us the area under the curve f of x from point A to point B. So, for example, let's just say we have our coordinate axes like this, and then I'll just draw some random function here, and we'll say that this is A and this is B. Then evaluating the integral from A to B of f of x dx, that will give us the orange region. So that will give us this entire area. And now we can see how these integrals relate to Riemann sums. If you remember, when we learned about Riemann sums, we were interested in finding the area under a curve, and we used a bunch of tiny rectangles and tiny trapezoids to find the area. That's exactly what we're doing here. We're finding the area under the curve, and we actually kind of are using tiny rectangles and tiny trapezoids, but we won't really go into why that's the case with this. Essentially, it comes down to this dx being a very, very tiny width, and we're evaluating the function at all of those points. And this integral is actually like a summation of all of those rectangles. So that's sort of the relationship. But yeah, this is the great thing about definite integrals. We're able to find this area underneath of a curve. And so yeah, the only difference in terms of what they look like is definite integrals have these bounds. So let's just take a brief moment to dissect a definite integral, and much of this should be familiar. So when we see this, we say that this is the integral from A to B of f of x dx. A and B are called the limits of integration, which makes sense. They tell us the limit of where we're integrating from. The area is bounded by those values, so those are the limits. And as we said, evaluating this integral will give the area under the curve f of x from A to B. And my favorite part, when we evaluate definite integrals, we do not need the plus c, and we'll see why that's the case momentarily. And also the thing to note is that areas above the x-axis are considered to be positive, areas below the x-axis are considered to be negative. So for now, we're mostly going to be dealing with regions. Actually, I won't continue with that sentence. But yes, this is the convention to follow. Above the x-axis is positive, below the x-axis is negative. Wonderful. So with that brief understanding of what definite integrals are, let's try to evaluate these definite integrals. So we have a graph of f of x, and we have like the areas within certain sections of this graph. So first we want to find the integral from 0 to 1 of f of x. By definition, that is the area under the curve f of x from 0 to 1. So if we look in our graph, 0 is here, 1 is here. So the area we're concerned about would be this red area. And that's given to us to be 2. Okay, so now we want from 0 to 4. So that's from 0 and 4. Well, this is 2, this is 3, so this should be 4 here. So the area we're interested in is, I'm drawing over this red now, but it's going to be this entire yellow area. Let me try to get rid of the red. But we can see that that yellow area can be composed of two separate sums. That's the area from 0 to 1 plus the area from 2 to 6. So this is, or from 1 to 4, which is 6. So 2 plus 6 equals 8. So that's that definite integral. Okay, next we want from 1 to 6. So let me just erase some of these. So we're starting here, and then 6 is over here, so we're ending here. So the area in question is this pink area. And remember, the area is bounded by the x-axis. So when we say under the curve, although like this area is like above the curve technically, we're just looking at the area between the curve and the x-axis. So again, we can like kind of split things up here. We know that this area is 6, and this area is 3. So we can say that this definite integral is, 6 plus 3. However, we should remember by convention, areas above the x-axis are considered to be positive, and below the x-axis they're considered to be negative. So really, the integral is 6 plus negative 3, which is equal to 3. Wonderful. Now we want to do from 4 to 8. So 4 is here, 8 is here. So that would be, what color haven't I used? Green. That would be this total area. And again, we can split it up into sums. So we have this area and that area to sum. This area should be treated as negative since it's below the x-axis. And this second area should be treated as positive since it's above the x-axis. So this would be negative 3 plus 7, which is equal to 4. And note that we're at 8, and we're given like this vertical line here at 8, so we're good on that front. And lastly, we want the integral from 0 to 8. So, where's my eraser? Now we're looking at basically the entire region. So I'll go back to red. That would be this, 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 and that. And so once again, we can break it up into chunks. The first area is 2. Second one is 6. Third one is negative 3 since it's below the axis. Last one is 7. Summing this together gives us 12. So that's a brief introduction to how we compute definite integrals when we're given the areas under a curve, but obviously we're not always given that. We have to compute that on our own sometimes. So keep in mind how when we had this like integral from 1 to 6, which was from here to here, we said that that integral, we could just compute the area from 1 to 4 and add to that from 4 to 6. We broke it up at some point in between 1 and 6. that idea is going to be very helpful in just a moment. Let's look at some properties of indefinite integrals. If our function is defined at some point f of a, then the integral from a to a of f of x equals 0. Let's take a moment to think of that pictorially. So let's say I want the definite integral from 7 to 7 of f of x dx in this graph. So 7 is right here, so that's where we start, but then we also end at 7, so the area we're trying to find is of this line, but as we know, lines don't have an area, so it's got to be 0. So that's the pictorial understanding of why the first property holds. Second one, if f is integrable on the entire interval a to b, and c is a value such that a is less than c less than b, so that means a is in between this interval, then the integral from a to b of f of x is equal to the integral from a to c of f of x plus the integral from c to b of f of x. So that seems a little bit complicated, but if we scroll back, that's exactly what I was mentioning just a moment ago. Here, let's consider a to be 1 and b to be 6. Then consider c to be 4. Then what that property is saying is that this integral is equal to, let me write it out, the integral from 1 to 6 of f of x dx is equal to the integral from 1 to 4 of f of x dx plus the integral from 4 to 6 of f of x dx, which is the property that we implicitly assumed to be true when we were computing these areas. We said, let's take this area from 1 to 4 and add to that the area from 4 to 6. So that property does hold for integrals. And note that this 4 could be, these two 4s could be like 5 or 2. The only thing is that they have to be in between 1 and 6, and these must be the same value. So yeah, I could have chose like 3 instead, but we don't really know the area from 1 to 3 or 3 to 6, so we chose 4. Okay, that's the second property. Third property is saying if we have the integral from a to b of k times f of x dx, where k is a constant, then that is equivalent to saying k times the integral from a to b of f of x dx. So those constants factor out of our integral. So yeah, those are the properties that we should be familiar with. This third one should be somewhat familiar from indefinite integrals, but the other two are a little bit, they're newer because now we're really considering areas. So these are the ones we want to keep in mind. Wonderful. A couple more properties, and these kind of follow from indefinite integrals. So if we have the integral from a to b of the sum of two functions, then we can break it up into the sum of the integrals of their individual parts, just like indefinite integrals. Next, we have just properties of how area works. So if f of x is an even function, which means it's symmetric along the y-axis, then the integral from negative a to a of f of x equals 2 times, this should say the integral from 0 to a of f of x dx. Let's just take a moment to look at this pictorially. So I will sketch some axes here. Whoops. That's an x-axis. Yes. There we go. Something like that. And we want a function that's symmetric along the y-axis. So let's consider a parabola that looks something like this. Actually, let me just make it wider. Right, that's roughly symmetric along the y-axis. So this property is saying if we start our integral at some point here, which we call negative a, and we go up to a, so we're trying to find this pink region. So the property is saying pink is equal to 2 times the integral from 0 to a. So let's color that green, I guess. This. So that's saying the property is saying pink area is equal to 2 times the green area, which makes sense, right? Because this green area appears on the left side just in reverse. So we can use this property if and only if our bounds are negative a and a. So it could be like negative 3 and 3, negative 7 and 7, something like that. But it can't be something like negative 2 and 5. They have to have the same magnitude. Okay, so that is that property. Now, if f of x is an odd function, which means it's rotationally symmetric by 180 degrees, then the integral from negative a to a of f of x dx is equal to 0. So what's a good example of this? Let's try to draw our axes again. So we want a function that is symmetric 180 degrees around the origin. So let's consider perhaps something that looks like this, some sinusoidal curve. So this is roughly a sketch of negative sine of x, kind of. But we can see that if we were to take this entire curve and spin it 180 degrees, it would be the same curve. So just to draw this out, let's just consider one point. If we spin this 180 degrees, it'll end up here. If we take some point here, spin it 180 degrees, we end up here. And we can see that there's this like circular pattern that's occurring. So all these points will line up on top of each other. So it is indeed an odd function. That's what we call odd functions to be. Okay, anyway, so this is saying the integral from negative a to a of this function is equal to 0. So let's just say this is negative a, and then positive a is something here. So then this pink area, the property is saying the pink area is equal to 0. And this is due to the symmetry of the function. It's rotationally symmetric by 180 degrees. So this area is identical to this. And it just so happens that any area above the x-axis on this side will be below the x-axis on this side. And similarly, any area that's below the x-axis on the left side will have a corresponding part above the x-axis on the right-hand side. So these properties are handy to know. Be familiar with odd and even functions. It's a very important classification of functions to understand. Wonderful. Let's move onwards. So we have our first open-ended question, kind of. So we're given two integrals from 2 to 4 and from 2 to 6 of the same function. And we want to know what is the value of the integral from 4 to 6 of f of x dx. Well, let's write it out. So the integral from 4 to 6 of f of x dx. How are we going to find that? Well, let's try to use the other integrals we have. We should remember that we can break apart integrals. Woo! Thank you for visiting, Karina. Thanks for coming back. Happy to see you. All right. So, we should remember that when we have an integral, we can sort of split it up based on a value in between the bounds. So, for example, from 2 to 6, we can choose like 3, which is in between 2 and 6, and then say that this integral is equal to the sum of integrals from 2 to 3 and 3 to 6. So instead of 3, if we choose 4, then we can say that the integral from 2 to 4 of f of x dx plus this integral equals the integral from 2 to 6 of f of x dx. And luckily, we have values for these red integrals. We have that this is equal to 5, And then we're still trying to find this integral here. And then on the right-hand side, we have -6. So we can subtract 5 on both sides, and we get the integral from 4 to 6 of f of x dx equals -11. And that's our answer. So that is a good application of the properties of integrals. Let's move onwards, and we have another graph question. So you can see that with indefinite integrals, there's a lot of graph questions because it relates to finding the area under a curve. So, a bug begins to crawl up a vertical wire at time t equals 0. The velocity of the bug at time t, where 0 is less than or equal to t, less than or equal to 8, is given by the function whose graph is shown above. What is the total distance the bug traveled from t equals 0 to t equals 8? Okay. So, we have to review some of the things we learned from physics while we were studying calculus. We mentioned a little bit about physics when studying derivatives. So what do we remember about how physical quantities are related to each other? We should remember that velocity is like the derivative of position, and like acceleration is the derivative of velocity. So now we kind of know what how integrals relate to derivatives. Integrals give us the antiderivative. So if velocity is the derivative of position, then position should be the antiderivative of velocity. And it is. Well, kind of. The antiderivative of velocity is actually displacement, which is the change in position. So that seems like it could be helpful, except the problem asks for the total distance the bug travels, not the displacement necessarily. So we can obtain the distance by finding the total area under the curve. However, the area under the curve would give us displacement. To account for distance, we just need to treat everything as positive. And this might seem a little counterintuitive at first, but let's think about it. If we go from 0 to time t equals 6, on this graph, we're strictly above the x-axis. So if we compute this area, it'll give us displacement, right? And the velocity was always positive, which meant that the bug continued crawling in the same direction up a vertical wire. So from t equals 0 to t equals 6, the movement of the bug, the direction it was traveling in, did not change. However, from t equals 6 to t equals 8, our velocity is negative, which means the bug went up and then it started crawling back downwards at time t equals 6. So, if we compute this area, that will give us both the displacement and the distance traveled. Thank you, Corinna, for the host. Much appreciated. If we take the area under the curve from t equals 0 to t equals 6, that will give us the displacement of the bug because it's only traveling in one direction. It's going basically upwards the entire time. So that'll give us both displacement and distance. But then when we approach from 6 to 8, this area is negative. So when we add it back to this one, the overall area is going to be smaller than just this. So if we think about the bug's travel, it goes up, and then it comes back down a little bit. So the total area would be measuring this displacement. However, we want really this arrow plus this arrow upwards, right? We're trying to find the total distance. So if we treat this as positive, that would give us total distance. Really long, drawn-out explanation of why that's the case, but take some time to think about why that's true. So let's find the total area. And we can partition it from 0 to 6 and then 6 to 8. So we'll start with this. So red is equal to the area of a trapezoid. So that's 1/2 the average of the bases times the height. So the first base is this bottom one from 0 to 6. And the second one is this top base from 2 to 4. So 6 plus 2 times height would be this height here, which is 3. And if we compute that out, we get 12. And then we have to compute the area of this blue thing here. So blue is equal to the area of a triangle. So that is 1/2 base times height. So in this case, the base goes from 6 to 8, so that's of length 2. And then the height is simply just 1 by the graph. So this gives us 1. So our total distance is equal to 12 plus 1, which is equal to 13. So that's choice B. If we were trying to find the displacement, that would be equal to 12 minus 1, which is equal to 11. So with displacement, we treat this as negative. With distance, we treat it as positive. Okay, great. That is our physics application for the day. Actually, not for the day. There might be more questions. I have to remember what my lesson plans are. Goodness. Okay, actually, here we go. Another physics problem. A particle moves along the x-axis. Its initial position at t equals 0 seconds is x of 0 equals 15. The graph below shows the particle's velocity, and the numbers are areas of the enclosed figures. So let's just label our axes. Here we have velocity with respect to time, which means the x-axis is time. What is the particle's displacement between t equals 0 and t equals c? So displacement is equal to the area under the curve. Displacement equals area under curve. And that's going to be equal to this 4 plus 5 plus negative 24. But since we're dealing with displacement, we do have to consider whether or not these areas are positive or negative. So this will be negative 4 plus 5 plus negative 24. This should be equal to negative 23. Now we're asked, what is the total distance traveled by the particle in the same time period? So now we treat everything as positive. So distance is equal to, in fact, I'm going to write it with absolute value signs. So now it's the absolute value of negative 4. I don't need the parentheses. Plus the absolute value of 5, plus the absolute value of negative 24. Treat everything as positive. That's equal to 4 plus 5 plus 24, which is equal to 33. So that's our distance. Okay. Give the positions of the particles at times A, B, and C. Okay. Do I have enough room for this? No, I don't. Let me add a page. And we will copy the graph. Copy, paste. Okay. We want the positions at A, B, and C. So at A, the position or the particle is at a point which has, like, we can find the displacement that the particle has achieved from t equals 0 to t equals a. That'll give us some displacement value, but it's displaced from where it was at t equals 0. So the displacement from t equals 0 is the area under the curve. From t equals 0 to t equals a. Since we're dealing with displacement, we do have to consider it being positive or negative. So this area is equal to negative 4, right? We're just looking within this bound, so that would be negative 4. So then its position at t equals a is equal to its position at t equals 0 plus displacement. Because displacement is measured from t equals 0 to the time it is now. We're given that at t equals 0, the position is 15. X of 0 is 15. So this is going to be equal to 15 plus negative 4, which is equal to 11. Okay, now let's do part B. We can just use our formula. We don't have to write out much of what I wrote before. So position at t equals b equals position at t equals 0 plus displacement. Oh, that's not how you write that word. Displacement from t equals 0 to t equals b. So this is going to be equal to 15 plus displacement. Once again, we have to consider area under the curve. So now we're looking from 0 to b. So that would be negative 4 plus 5. So negative 4 plus 5. So that will be equal to 16. And then for c, I'll just abbreviate x at time c is equal to x at time 0. So x is just position plus displacement from t equals 0 to t equals c. So this is equal to 15 plus displacement, once again, area under the curve from here to here. We have negative 4, we have positive 5, and we have negative 24. So this will be negative 4 plus 5 minus 24. And if we compute this out, we get negative 8. So just like that, we've computed the position of the particle. And notice how we needed this initial condition, where it started out at. And that makes sense, because if we didn't know where it started out at, well then how would we be able to tell where it is at other points in time? So yeah, initial condition needed. Okay, and then approximately where does the particle achieve its greatest positive acceleration on the intervals 0 to b and 0 to c? Okay, so we're looking on this interval here first. Let's just look. I'll draw it out with my pen. And we're asked to find where does the particle likely experience its greatest acceleration. So bear in mind that our graph is velocity in terms of time. And from our education on derivatives, we should remember that acceleration is the derivative of velocity. Let's write that out here. Acceleration is derivative of velocity. So the question is really asking us, on this interval, where is the derivative of the function likely the greatest? Well, derivative is slope of the tangent line, so we want some part on the function which has a really high slope. So if we look in the beginning, this slope is negative, so that's not very good. But then around here it reaches 0. And then it starts to get more positive here until it starts flattening out. So the slope here is, like the slope at A is quite positive. And this slope is actually greater than this second line that I'm drawing, the slope at the second line, just because it's a steeper line. The first line is steeper. So here the slope is still positive, but it's less than before, and then it's 0, and then smaller. In fact, here it's a negative. So the greatest slope probably occurs somewhere around A. That's where we would approximate it to be. And then we want to know from A to C. So we're looking here. And once again, we want to look at the tangent lines, and we can sort of eliminate like this part of the curve because it's decreasing, so we know that the tangent line will be negative. So the only new part of the curve we have to consider is like this part of the curve. And towards the end here, the slope gets pretty steep, and if we compare it to A, perhaps at point C, it's a higher slope. So maybe we would expect the acceleration to be greatest near C. So here, for 0 to B, it would be near A, and for 0 to C, it would be near C. Right? We're just approximating where it would be. So yeah, it's good that we reviewed a little bit about derivatives, but now we can see how all of these physical quantities are related, not only in terms of derivatives, but also antiderivatives, integrals, things like that. Great. So that is that.